Okay, let's go over this FP question from 2022. So in this question, we are given a data tree of A of B is tree of A of B of this thing. So this is just I don't remember what kind of tree it's called, but it's the tree where it's like it has a key, a value, and its children, sort of that idea. So A would kind of be the key, B would be kind of its value, and then whatever the tr list of trees would just be sort of its children or what are linked to it. Will be used to store a relation between type A and type B. A search of this tree will then implement as a function from A to B, returning the first value of B found related to given A. So in part A, we're asked to define a function DFS, which returns a list of all the B values related to a given A value in the tree in the order which they would be found by a DFS search. So for this, for DFS, what we do is, so like this is our data type tree. So then we have our DFS, and there it gave us a type. We have equality, and then we have first A, then a tree of A of B, and then we're trying to output a list of Bs, right? That's related to A. So we're going to write the definition directly. A, we're just going to call T. So like this is our target value, and then we have our tree, which is broken down into having parts of A, B, and children's. So like I just did CS for short. So I'm going to check if T is equal to A, so hence basically if our A value is our target, then basically we would add the B value in the front of the thing, and then the remainder of that would be concat map of calling DFS on the children, right, list. Otherwise, we would just concat map of the whatever list is remaining. So it's just whether or not to add B in this case. In part B, we're asked to find a function BFS, which returns a list of all the B values related to the tree found by a breadth first search. And then the hint asks us to consider first writing a function which does BFS, whose roots are considered next in the order which they appear in the list. So hence the idea of BFS is that we kind of have to store it in the order of something that happened in a waiting list before we kind of process it, right? So we're going to have to write a helper function for that, and then just call the main function what's called the helper function. So here we have BFS, the type is the same as before, BFS, or have our target and our tree. And we're just going to call our helper function BFS list, and we're just going to give it a tree, where basically if it was empty, then we just return empty because there's not much to do for that, right? And if BFS list was a tree, the first element would be a tree, right? The first one we deal with it, and then the remainder is that waiting list we're talking about. So if it was the case, then we just have the B in front, and now we're going to call the remainder of the thing as well as adding C to the thing, like its children. I should have wrote CS, but yeah, I should have wrote CS over here. This was a mistake on my part. So over here, this should have been CS, and this one would have been CS as well. So the idea behind this is, okay, basically, I have my waiting list, right? I'm just going to take the first element of the waiting list that has been waiting the longest, and I'm going to process it in this order. I'm going to check that if it's equal to A, the target, I mean, if it's equal to T, the target value, then I'm going to add B to the thing. Otherwise, I just wouldn't. And then I'm going to add whatever children it is to the back of this list by just the plus plus sign. And I'm just going to call it like that. So that's the idea behind this. And initially I called BFS list and I just gave it my tree. So the idea behind that is, okay, if I have this tree, that would just be what I start off with, right? So I just give it to that. Mm, and that would be the first one at the root. And then part C, we're asked the edges of a graph with nodes labeled by value of type A might be given by adjacency function A, the list of A, which returns for each node a list of the adjacent nodes. For part C, we're asked, given such a function, write expand this type, which constructs an infinite tree whose root represent an initial source node, and in which the children of each node of the tree correspond to adjacent nodes of the graph. The tree relates to each node of the graph reachable from the source to a not necessarily simple path from source to that node. Okay, so basically we're just asked to write a tree like that could be potentially infinite, right? So we're going to look at the sort of what we're asked, because we're given the type, right? So A, the list of A, that means that we're just trying to find all the neighbors of it and give it in the list. So if we were to input a node, then it would just give all the nodes that are neighbors to it in the list. And now we're going to input a node, and now we're going to hope to get out the tree of it. We're just planning to get the tree of the whole thing, right? A is our source node where we start off, and then we hope to build a tree from that. And then the tree could be infinite in the case that, let's say, there was a cycle, then if we're in that cycle, then it means that the tree is going to be infinite. So how we're going to write this expand is we're just going to call adjacent, which would be our function that takes a node and just gives out the neighbors of it. And now we're going to have our source, which is basically our original node of the root. And we're going to use a helper function again because we can't build this from scratch, right? So we're going to call build t of source with source. What that means is build t, I'm going to have a node, I'm going to have a path. For the node, what it means is where I am at right now, right? If I'm calling it at the base case, I'm at source. And then the path is just whatever path that I took to get here. So if I'm at the source, then the only path that I took to get here was getting to here, right? So that would just include source. So that's why this would be my base case of calling it. And my build t of node path equals tree of node path. And then I have a list of the children's, which I would build by just doing build t of the child of the path plus the child, list of child, where my child is just every child goes from the adjacent node. So that I have many of the trees stacked in the list of the children's. So yeah, so that's how I would build it recursively. Is first, okay, I have a tree. I'm going to define a tree, right? And then I'm going to have the node, the path, and then the children would just be each of the children going through it by the child is the adjacent node. And then from there, going from adding the child to the path, end of the path, and then making sure that I call build so that I have this extra section to it. So that's C. Part D, we're asked, let's go back to part D. Basically, we're given some more info. A word ladder is a sequence of 5-letter words where each differs from the previous one by exactly one letter. For example, the ladder adder, aider, writer, riper, viper, at basically is just changing one letter at a time. So in part D, we're asked to find a function adjacent which determines whether two lists differ in exactly one place, and we can assume that they have the same length. So for part D, what you can do is do something with basically first pairing up with zip, right? Every element, if we pair it up with zip, that would be easiest. And then we're going to filter out the ones that are the same. Then we're just going to check the size of the remaining is equal to 1 or not to see if there's anything that's different. So adjacent, this was the type they give us. We're given a list of A's, and then another list of A's, and we want to compare the two lists to see if they're the same, if they have exactly one in common. So we're going to output a bool. Adjacent of x of y's, we're just going to do, what we're going to do is first zip it up together with zip x's y's, right? And then next what we do is we just map it into x of y. And then we check the condition that x is not equal to y. This would be our filter condition. And if it wasn't the case, then we don't care about what the value is. So we're just going to drop it. So we just insert just a placeholder there to count the number. And then we're just going to use length at the end to check if it's equal to 1 or not. So part D is really straightforward, I'd say. And then for part E, we're asked given the list of words, strings representing five-letter words, to find a function ladder that basically finds a shortest ladder from one word to another if such a path exists. I think part E is probably one of the harder sections of this thing. Basically, what it tries to do is tries to find the neighbors, build a map of all the route, search for destinations, and finally return the shortest. If it finds any, it would be the shortest because we're going to use BFS to get the shortest path, right? DFS is not going to work here, so definitely because we're trying to get the shortest. And just so you know, on like the types, we're given a list of chars, another list of chars, and then we want to output a maybe of this type. Why is it maybe? Because in the case that, like, let's say there wasn't a path, right? We want to return something that indicates that it's not possible. But if we're restricted to doing a nested list of chars, then that's kind of restricted. So rather, we just do maybe so that we can return nothing instead to show that's not possible. So we're going to define ladder to be having two kind of parameters, start and target. And we're just going to do a let in statement. So let basically does all the definition and the in is just our final checking. So we're going to define get neighbors. Current W is equal to um, this thing over here. Why do I need the get neighbors, right? Because I see that over here, I would definitely want to make the tree. So if I want to make the tree, I need to use the expand function. But earlier I see that expand function requires, basically I need a function that takes a single input and maps out to a list, right? But I don't have this function here, so I need to define it myself. So that's why I need the get neighbors function that I'm defining here. I'm just going to call it the current words is equal to the candidate words. And then the candidate words come from basically going through all the words that from words I get the candidate words. And I make sure that the adjacent, I call the adjacent function, and then the current word is equal to the candidate word. So I make sure that these are the same so then it's possible, right? And then we just give the list of words. And hence from there, what I can do is I can just expand and I use my helper function that I just wrote. Basically, this is like the adjacent function. And then I have the start. Basically, that would be where I start off. And I just call this to be the all possible paths tree, where this is just a tree that's there of all the possibilities, right? And then what I do is I want to call BFS. So I'm going to call BFS, and then I have my target, and then I'm going to have my tree, right, of the paths. And then I'm going to set my successful paths to be, if I find any, all of it would be stored in here. And then what I can do is, I have no successful paths, then I return nothing. Otherwise, I would just return the head of the successful path, which would be my shortest path from the BFS, right? So yeah, that's my part E. Um, and then for part F, let's go back to F. What does your function return if the starting word um, is one which has no neighbors? What does it do if the words involved all have neighbors, but the starting and ending words are in different components of a disconnected graph? So we're dealt with two different conditions, right? So in the two conditions, we can kind of talk about it. If the starting word has kind of no neighbors, then we're going to have to expand it, in which we get a single root tree because it's only that word. And then BFS would find no match, so it would return an empty list. So then we check our condition. If it wasn't no, then we'd return nothing, so we'd return nothing. And if a graph is disjoint and it has cycles, it means that on one side we could get caught into the thing, into an infinite loop and never get to the other side. So the program would just hang and not terminate over in this condition. And in part G, we're given where there are gross inefficiencies in your program, suggest some ways that its performance might be improved. And we're not asked to implement them, just suggest them. So basically, there are some kind of bugs in our things, like not the best. So definitely the infinite loop case is definitely wasting a lot of resources by just computing it, right? Even though we're just saying that Haskell is lazy, it's still better to kind of keep track of it by the visiting nodes that are already visited so we don't make sure we don't repeat ourselves. On top of that, another improvement we can make is kind of making it faster because many of the queues that we're doing, we're just doing plus plus at the end. And that means that we have to go through the left, all of the left, and then just add one more element to it. So then our complexity would be O(n) squared, which would be very bad. So we can use probably a better data structure for that, um, perhaps sequence. Another way of doing that would be just for pathfinding. We're doing the same thing, right? Adding plus plus each time. So instead, what we can do is use cons and then at the very end, reversing the order so that we get what we need. And it would be more efficient this way, especially if the list was long. So that we don't make sure that it's still O(n) rather than O(n) squared, right? In terms of complexity. And one more thing on top of that was just a clarification that I made in terms of um, understanding the thing, but I'm kind of having trouble finding where I kept the notes on that. So let me search for it. In the meantime, otherwise, hmm, can't seem to find it. It was basically the idea that inside here there was um the tree that was kind of difficult to. Did I store it in another place then? Let me check. Yeah, it's not stored here. Okay, I'm gonna try to find it right now. The idea is basically, it was kind of confusing at some point of the data tree AB equals tree of AB, tree AB. So the idea behind this is just that on the left-hand side, the tree is different from the right-hand side of the tree. One is like telling you of the type, and the other is actually just telling you of like the function we're defining, like the data constructor that each one is following a data constructor. Let me try to find my history for that. I'm so sure I wrote it down somewhere, but I can't seem to find it anyway. Okay, never mind, it's here. I'll just upload it to my computer using my phone, and then we can go over it. I think it's much easier to see it visually than have to kind of explain it, the concept without anything concrete. Wait, where was this thing? Um, Okay, so this was what I was talking about. Basically, over here in the thing when we were defining the data type, we had something of this form, tree of this. So basically, on the left-hand side, basically the tree means tree of type. Like it's called like tree type. It's just the same name because it's shorter and easier to write. But basically, the more intuitive kind of thinking process would be to treat this at the left-hand side thing as a type of the parameters are A and B, which could be string or int or whatever it is, right? And then on the right-hand side, that tree basically means tree make node. It's just like a function, actual function. And it has three kind of data constructors. It has A, B, and then we're going to call this um, another thing of tree, right? Of type tree type of AB. So this is the idea is that basically it's this tree is not these two trees are the same concept and this tree is kind of its own concept. it's kind of important to differentiate it between the type and actually the kind of like the function constructing the data. So yeah, that brings me to the end of this. I think this chapter was relatively on the harder side because there was quite a few concepts with the DFS, BFS, and just solving the problem in general. But I think it was definitely a good question to do. End it off here.